We have a little bit of time. Let's get into chapter 2. What does chapter 2 deal with? Well, it's a lot of review of vectors, isn't it? And then, what do we use vectors to describe? Forces applied to our objects. So the whole chapter is dealing with force vectors. It's a lot of math. What's that? Math. And if you weren't great at it, well, you have to bone up on it. So did you ever have a class in geometry? Angles and lines and, oh, this angle is the same as that angle down here. You ever have a class in trigonometry? We're not going to do a lot of differentiation, but at the end of the semester, not in this chapter, we'll also do a lot of integration. But trigonometry is huge in this chapter. Let's jump into it. You see a word, and to me, when I'm confronted with a new word, I want to understand the word. Well, how did this word even come into being in our language? That's the study of etymology. So etymology is the origin of words. True? So somebody says, we're going to study scalars. That's kind of a peculiar word, scalar. What's the etymology of the word scalar? Because we have scalars and vectors. Have you ever heard of scalars and vectors before? Sure. What is the etymology of the word scalar? Well, you can now, you don't even need to go to a dictionary. You just type it in the Google, and it's coming from Latin, scala, and it goes all the way back to something like a ladder, to scale. But ladder has well-defined steps, hopefully at equal increments. You ever tried to go up steps that are not equal increments? They are a super trip hazard. All right? Equal stepped ladders make sense. Let me continue on. So here's another definition. So it represented by a position on a scale or on a line, having only the magnitude, which is important. That's a scalar variable. That's how they use the word in engineering. Oh, it's a scalar. Well, what's the other one? Vector. All right, you can do the etymology of the word vector. It goes back to some Latin, okay. It's something about to convey, moving from some origin to some ending, beginning to ending. It's convey. That's the idea in the Latin for the word. And then you say, okay, take a look at magnitude and direction. So vectors have not just magnitude, that's scalar only, but also direction, like going from here to there. And you can think about lines and points, but we've used vectors to represent a lot of things. But the idea is conveying or moving or displacing from one location to the other. List. This is not a clicker. We could do the numeric and alpha. We could do that, but let's not do it. I'm going to just walk around. You have a sheet of paper. You have a pencil. Please list some things that you describe as engineering and science with scalars. It's not that hard of a question. And then once you have it, divide the sheet like this and make a list of things that are described in engineering and science by vectors. And I want to walk around and see your list. All right, so I'll take a little participation, some person that's not too shy and doesn't feel like I've abused them yet too much in this class. Give me one scalar. Speed. Okay, and the cousin of speed, which is often described as a vector, is velocity. That's right, absolutely. Another one. Yes, sir. Time. Time is definitely a scalar. Yes. Did you have? I was going to say time. You got time too? All right. Anybody else? Temperature. Temperature scalar. True? All right. Which one? Weight. That'll work. How about density? Where would you put density? Density is a scalar. Is that the same as pressure? Pressure. Yeah, you could talk about the magnitude of pressure. Once you have an orientation, it then could be described as a vector as well, because it would be perpendicular to a given area of interest, but pressure is often just a scalar. All right, you had one? Length. Length is a scalar. How about some vectors? Yes, sir. Force is a very good one. And guess what? Our chapter title, you know, even if you do this, say, okay, I'm studying this chapter 2. What chapter am I in? Chapter 2. What's the title of chapter 2? Can you remember what it was? Force vectors. There you go. Little clue. Helpful, right? Believe me, test yourself when you're studying. Say, I don't even know what chapter I'm in. What's the name of the chapter? Shut the book. I know you can read it. Shut the book and test yourself. Say, I think it's 5 minutes later. Okay, test yourself again. Force vectors. Good. That keeps you on track. Anybody else on a vector? Yes, sir? Acceleration. Because it's the magnitude of it. We know the direction at which it is. You can express weight as a vector force. You're absolutely right, you can. So you would have pick a coordinate system, and maybe this is Z, and then G is going down that way, and then the weight could be a vector, right? And so nothing in IJ, but something negative in the K. All right? I'm getting a little ahead of myself. All right, you've already participated twice, so I'm going to try and get some of your friends. Yes? Moment? Wow, you're already in dynamics. So, yeah, so when you have rotational moment, right? Okay. Oh, moment of a force, sure. Displacement, those are all could be described as vectors. Yes, sir. Friction. Friction is typically a scalar, and you assume the direction based on it, or you multiply by the magnitude of friction and then put it in that as a vector. You could either way. Some of these you can make them go like weight, could be both of them.
What about tension?
Tension, let's move on. Name something that is described by a scalar vector that's probably not on the list of other students in the class. Now it's really challenging. You mean I've got to go beyond mass and length and time? Yeah, that's the low-hanging fruit. Now get up to the top of the tree. Somebody says, moment of a force. Excellent. What were you just saying? You know, something else. I anticipated this next. Go ahead. Which one? Okay, what do you got? Watts? That would be, you mean like power? That's a unit to measure power, right? And I think power would be a good scalar, right? And then vector, I think watt or power is a good scalar, right? So are you thinking it's a vector?
No, I thought you were asking.
Yeah, so do you have a vector? No, your friend back there does. Shear force? Sure, shear stress? Yeah, you could express it as a vector. Yes? Centrifugal force? Yeah, so it's coming in. Here's the point, going mass that's directed like that, changing all the time. Like an impulse? Change in acceleration. A jerk, is that what you said? A jerk? It's like a impulse. Impulse leads to a rapid change in linear momentum. Linear momentum, there it is. Linear momentum as well as angular momentum are good vectors. All right.
What about gradient?
Gradient. So if I have a temperature field and it's hot over here and it gets cooler, and then I could take the gradient of that scalar temperature field and that will produce a vector field. The gradient operator of a scalar field. You're taking EA2 or something probably. So there you go. Yes, sir. Resistance typically would be a scalar. Yeah. All right. Well, when you think a little bit outside the box, and then that helps you learn to push the envelope. Okay, in this textbook, what is our standard notation used to identify a vector? And those that have the book open have a little advantage, but if you can recall from memory, that's even better. What is our standard notation in our textbook for what is a vector quantity? Anybody? It is like big F, but it's bolded, bold. True? Or A, but it's a bold A. True? All right. When you have handwritten work, it's like a dichotomy. Oh, if it's in print, it's this. But if it's handwritten, what is the standard notation to identify a vector? Little arrow. So you have F or A. True? And so this is kind of like, am I in print or am I doing it by hand? It's very hard to write bold letters, cap letters, bold, that are for vectors, handwritten work. Well, you've all done things with vectors. You've multiplied by a scalar. So if I had the vector A, could I multiply by a scalar C? Will that give me a new vector? The direction of it doesn't change. What happens to it? The magnitude, the length of it. That's right. So if C is greater than 1, what did it do? If C is between 0 and 1, what did it do? What happens if C is less than 0? It's negative. Can you have a negative number that you multiply the vector by? It flipped it. That's right. And now it can, be small, or just flip it, or be long and flipped. It depends if it's, let's say, negative 0.5 is the constant, negative 1, negative 2. So you can multiply vectors by a constant, a scalar. Can you take and add two vectors? Take the vector A and add it to the vector, let's say, B, and get a resultant vector C? Yep, sure can. Can you subtract? So A minus B equal to a new vector, different vector C? Sure can. We need to be able to do those. Now, if you're doing it graphically, guess what you're going to remember from trigonometry? I can't pronounce this word. Can you help me? Parallelogram. It's the, oh boy, this is why this class is hard. This is why this class is hard. You have to remember all this trig. All right, well, what's the parallelogram law? I'll take one volunteer. Somebody who hasn't said anything all day yet. Well, that's just like, go ahead. Yeah, basically do it in 2D only. So you can do it in 3D, but we're going to describe it in 2D. Let's say this is my vector A, and I draw it, and I have a vector B, and I draw it. How do I get a parallelogram? It's like two lines that are parallel and two lines that are parallel. And guess what is this? A parallelogram. That's what that is. And now we use it for addition or subtraction of vectors. And we say, oh, this is the side A vector. This is the side B vector. The resultant goes across what? The diagonal of the parallelogram. So the way you do it is you move maybe B conceptually over to the tip. So you put the base or the beginning of B at the tip or the ending of A. And then what does this give us? Just half of the parallelogram gives us a triangle. Oh, that trigonometry. And then once you have triangles, you have funny laws. Sine law, cosine law. For this chapter, they're your friend. You haven't seen them in a while. They just called you up. They're wanting to spend the weekend with you. And, yep, you're going to spend the weekend with them, right? It's a sine law and a cosine law. Who can, from memory without the book open, look at and draw? I'm going to walk around the room and see how you're going to do. Tell me what the sine law is and tell me what the cosine law is. Professor, I don't like this. You're requiring us to do stuff from memory. So typically they take a general triangle and they have interior angles and they give them some letter. Typically it's lowercase a, lowercase b, lowercase c. And then they have the lengths of the sides, and the length of the side, which is opposite the angle lowercase a, is given uppercase A. So uppercase A, I think about 5 people use this notation when I walked around the room. Is it not right? That would be the length. And then opposite from lowercase c, the side would have a length uppercase C. opposite of lowercase angle, interior angle, lowercase b would be cap b for the length. So we have to know what lowercase abc and then uppercase abc mean. And then the sine law would be a divided by the sine of a is equal to b divided by the sine of b and c divided by the sine of c. Is that our sine law? That helps us when you have these angles to determine, oh, I need to calculate this angle or I need to calculate this length. I use one of these equations. What about the cosine law? That would be, depending on how you want to write it, you want to write it in terms of this length c. C squared is equal to a squared plus b squared, but there's a minus 2ab cos of lowercase c. All right. Now, can I rederive that? No. That's why you took a whole class in trigonometry. I could rederive it, but I don't have time. There's certain, like, we're going to start there. And really, that's the meaning of this word law. It's like, I'm just going to start here and work forward. All right? There's a lot of work to get these relationships. All right. Now, once you have good description of what a vector is, know how to add, and subtract, how to stretch them or compress them and switch them by multiplying by scalar, how to calculate sides with using the parallelogram law, angles. Then you can describe forces with the vectors and then start adding the forces. Adding the forces. We need to do that in statics. So then we'll have a resultant force and then be able to bust the resultant force into particular components. This is a little challenging. Let me say very challenging. So please spend the time working on it. Let's move forward. Let's solve this problem. You have a plate. Has two forces applied at this A and B. So this is the subscript notation, force A and force B. All right. The line of action of B intersects with the line of action of force A. Can you see that? Where do they intersect? Right there. Okay. Okay. Determine the magnitude of the resultant force as if I'm adding these two forces together. Then I'll get the resultant force. What law am I going to use? The parallelogram law. Right. And then you want to calculate the direction measured clockwise from the horizontal. So this is our horizontal. And which way does the clock go? This way? Is that clockwise? Hey, I have a digital watch. I don't even have things that rotate in circles. No, I know. This is going to be, just like G sub C is archaic, maybe soon clock rotation will be archaic. I don't know. Maybe another 50 years it'll be archaic. But it'll be rotation from the horizontal clockwise, the direction for the resultant force. All right. And can I give you a little time to do that? So we ran out of time, and so I'm going to finish up this problem in my office. Basically, we had set up this problem. We had a point here where we had this force F of A applied as well as this force F of B applied. And then we think about these as being constructing a parallelogram. So the parallelogram would go like this and like this and like this. So these two lines are parallel and these two lines are parallel. And I know that I haven't drawn the length well, but the length of this line should be scaled to be a measure of like 9, even though we don't have units of length of kilonewton, but that's like the length. And then this length over here on this side would be 6. I didn't really draw it that well. So the resultant would be going from here across a diagonal of that parallelogram, and it would look like that. And then what we find is this is the resultant force F of R. We're asked to calculate the magnitude of that resultant force, and then the measure of its direction measured by the angle measured clockwise from the horizontal. So this angle right here, maybe we'll call that angle theta. So there's our parallelogram, and there's our length of the side, f of r, we want to calculate, and that angle measured clockwise from the horizontal theta. So we pick out, I like to pick out a, once I have the parallelogram established, pick out one triangle. Let's pick out this as our triangle to focus on right here. And what we'll do is we'll use either the sine law or the cosine law. Now for this angle, it looks like it might be 90 degrees in here for this angle, but it's definitely not 90 degrees in here for this interior angle. And this angle is unknown, and that angle is unknown. Now this angle right here that's inside is going to be 50 minus theta. So that's not a 5 theta, it's 50 degrees minus theta. That's that interior angle of the triangle over there. And we don't know this one either, and we don't know those interior angles, but we do know the lengths of the sides. The length of the side over here, let me try and emphasize it, this side is length of 9 in units, think of kilonewton, and then the length of this one on this side is 6 kilonewton, and then over here we're wanting to get the length of that side of the triangle, f of r, in units of kilonewton. Well, we stare at this a long time and we think, okay, the tools I have are the cosine law and the sine law. And after a while you deduce that I can probably figure out this interior angle easiest. Let me go to another slide. And so on this slide what I have is a little clearer, cleaner description of that triangle. The length of the side unknown, f of r, the unknown angle, the length of this side 6 kilonewton, the length of this side 9, and we really want to find this interior angle. Well, it's shown to be 105. How did we deduce that? Well, we go slowly. We come down here and we draw a horizontal line, and we have a horizontal line right there, and then this line and this line are parallel because they're the sides of the parallelogram. This is the line of action of that FA. Okay, so we look and we say, well, with respect to the horizontal, that was 25 degrees. Hopefully you see how we deduce that's 25 degrees. Then likewise we go and we say, well, from the horizontal, this f of a is sloped down 50 degrees, hence from the horizontal slope down 50 degrees for this f of a. So I have 50 and 25, that makes up 75 degrees, and I know that if I go the whole length all the way around, that'll be 180 degrees. So it's this angle, I didn't give it a name, but it's calculated to be 180 minus 75, and then that's our last angle. Of these three angles make up the 180. So that's the 105. So a little bit of work. Good old geometry helps us determine that angle right there. Now we use the cosine law, and so the length here, f of r, or I like to write it as f of r squared, is that's opposite of this angle 105. So it's the length of each of the other sides, f of b squared plus f of a, well, a I wrote, and then b squared minus 2, then the length individually, f of a, f of b, times the cosine of that angle opposite, which we just worked so hard to get, 105 degrees. Okay, and so we know the f of a, that's the 9 kilonewtons. We know the f of b, 6 kilonewton, minus the 2, this is squared, minus 2 times 9 times 6 times the cosine of 105. And then we would take the square root of all that, we get f of r. Okay, so I made that calculation. Let me just scoot down right below. And f of r, using the cosine law, comes in to 3 significant digits right at 12 kilonewton. Okay. Then the other is I need to get this angle theta. Okay, to finish out this problem and to calculate theta right up here, I need to use the sine law and first calculate beta, and then notice that this angle 50 degrees is the sum. 50 degrees is the sum of the unknown theta that I want to calculate, and beta something that I will calculate using the sine law. So theta, the answer will come in at theta is 50 degrees minus beta. Now how do I calculate this interior angle beta? Well, we use the sine law, and so the opposite to that angle is the side with the magnitude f of a. So f of a divided by the sine of beta is equal to the magnitude of this f of r side divided by the sine of the angle opposite it, which is our 105. And then we just check. We say, okay, I know that, I calculated it. I can calculate the sine of 105. F of a is known, it's 9 kilonewton, and it gives me the sine of beta. So the sine of beta is equal to the sine of 105. Whoops, let me kind of write that again. The sine of 105 times f of a divided by f of r, or beta is equal to the arc sine of the sine of 105 degrees times the magnitude fa divided by the magnitude fr, and close. So just make sure that your calculator, you can run that and you calculate that the beta is equal to 46.2 degrees, and then when you come up here, then you're going to calculate that the theta is equal to 3.78 degrees measured in the clockwise direction from the horizontal. And recall that we did calculate f of r to be 12.04 blah blah blah. It's down here to all those digits, but to write it to 3 significant digits, it's just 12.0 kilonewton, and place that in the box. So with that, I want to just note that I made a little typo right in here. I've just messed that up. It's the sine of 105 times f of a divided by f of r. So with that, we're done with this problem. Hope that helped. Thanks.